So you want to know if there's a theory of everything. It's one of the biggest questions you can ask. It's the kind of question people stare at the ceiling and think about at 3 a.m. It sounds like something from a science fiction movie. A single equation that explains the whole universe. Every star, every planet, every person, every speck of dust. All of it running on one elegant, beautiful rule. The short answer is we don't have one. Not yet, anyway. And we have no idea if we ever will. The longer answer is the story of the biggest search in human history. It's a story about two different worlds that don't talk to each other, and the scientists trying to build a bridge between them. To understand the search, you have to understand the problem. The problem is that physics, as we know it, is split in two. We have two sets of rules for how the universe works, and they are incredibly successful. They are the most accurate theories humanity has ever created, but they contradict each other. The first set of rules is for the big stuff. This is Albert Einstein's world. His theory of general relativity describes gravity. It covers planets, stars, galaxies, black holes. It's the physics of the cosmos. General relativity says that gravity isn't a force in the way we usually think of it. It's a curve in space and time. Imagine a flat rubber sheet. That's the universe. Now, put a bowling ball in the middle of it. The sheet sags. The bowling ball has curved the sheet. If you roll a marble nearby, it won't go in a straight line. It will follow the curve created by the bowling ball. It looks like the marble is being pulled toward the bowling ball, but it's really just following the bent path in the sheet. That's what general relativity says is happening. The sun is a bowling ball, the earth is a marble. The sun bends the fabric of space-time, and the earth follows that curve. That's its orbit. This theory is beautiful, it's elegant, and it works perfectly for describing the universe on a large scale. We use it to guide our GPS satellites. It predicted the existence of black holes and gravitational waves. It's a masterpiece, but that's only half the story. The second set of rules is for the small stuff. This is the world of quantum mechanics. It describes the universe at the level of atoms and the particles inside them. Electrons, protons, quarks. This world is nothing like the smooth, predictable world of Einstein. It's weird. Deeply, fundamentally weird. In the quantum world, things don't have a definite location until you look at them. A particle can be in multiple places at once. It's just a cloud of probability. When you measure it, it snaps into one position. Energy isn't continuous. It comes in little packets or quanta, and particles can be linked across vast distances, what Einstein called spooky action at a distance. If you measure one, you instantly know the state of the other, even if it's on the other side of the galaxy. Quantum mechanics is messy, chaotic, and based on chance. But just like general relativity, it works. Well, it's the foundation for almost all modern technology: computers, smartphones, lasers, nuclear power. All of it comes from understanding the strange rules of the quantum world. The set of theories describing these particles and their forces, not including gravity, is called the Standard Model. And it is stunningly accurate. So, we have two brilliant theories, one for the big, one for the small. What's the problem? Most of the time, there isn't one. If you're a cosmologist studying galaxies, you use general relativity, and you can pretty much ignore quantum mechanics. If you're a particle physicist smashing atoms together, you use quantum mechanics, and you can pretty much ignore gravity, because the gravity between two tiny particles is incredibly weak. The problem comes when you find situations where you need both theories. Situations where something is both incredibly massive and incredibly small. There are two places we know of where this happens. The first is the center of a black hole. A black hole is what's left when a giant star collapses under its own weight. It creates an object with enormous mass squeezed into an infinitesimally small point. That's called a singularity. To understand that point, you need general relativity because of the immense gravity, and you need quantum mechanics because of the tiny size. The second place is the very beginning of the universe, the Big Bang. The story goes that the entire universe, all the matter and energy we see today, was once packed into a point smaller than an atom. Again, you have something unimaginably massive and dense in a tiny, tiny space. You need both theories to describe it. And when you try to use both theories in these places, the math breaks. It completely falls apart. The equations spit out nonsense answers, like infinity. It's the universe's way of telling us that our understanding is incomplete. The two pillars of modern physics are telling us two different stories about reality. They can't both be right, at least not in their current form. This is the crack in our understanding of the universe. And a theory of everything is the attempt to heal that crack. It would be a single theory that works everywhere. A theory that contains both general relativity and quantum mechanics within it. It would be the parent theory from which our two current theories emerge as special cases. When you look at big things, it would look like general relativity. When you look at small things, it would look like quantum mechanics. But underneath, it would be one unified whole. Einstein spent the last 30 years of his life searching for such a theory. He failed. He felt the weirdness of quantum mechanics was a sign that it was incomplete. He famously said, "God does not play dice." He wanted a more deterministic, elegant reality like his own theory of relativity. But the dice-playing weirdness of the quantum world has been proven right over and over again. After Einstein, the search continued. And over the last few decades, a main contender has emerged. You probably heard its name, string theory. The basic idea behind string theory is simple and kind of beautiful. It says that if you could zoom in on the fundamental particles we know, like an electron or a quark, you wouldn't see a tiny zero-dimensional point. You would see something else. You see a tiny, one-dimensional, vibrating loop of energy. It's a string. Everything in the universe, according to this idea, is made of these tiny, vibrating strings. And here's the clever part. The way a string vibrates determines what kind of particle it appears to be. Think of a violin string. You can pluck it in different ways to get different notes. A C note, a G note. It's the same string, just vibrating differently. String theory says the particles of the universe work the same way. A string vibrating in one pattern looks to us like an electron. The same kind of string vibrating in another pattern looks like a quark. Another vibration looks like a photon, the particle of light. All the different particles and forces we see are just different, notes being played by these fundamental strings. It's an incredibly powerful idea. Instead of a whole zoo of different fundamental particles, you have just one thing to string. The universe becomes a cosmic symphony. What's really exciting about string theory is that when you work through the math, one of the vibrations it predicts corresponds perfectly to a particle we haven't found yet. This particle, called the graviton, is the hypothetical quantum particle of gravity. In other words, string theory doesn't just accommodate gravity, it requires it. Gravity naturally emerges from the theory. This was a huge moment for physicists. It looked like the first real bridge between the quantum world and Einstein's world of gravity. It seemed to unify all the forces of nature in one framework. So, is that it? Is string theory the theory of everything? Not so fast. It comes with some serious baggage. The first major hurdle is that the math of string theory doesn't work in the universe we know. It doesn't work with 3 dimensions of space and 1 of time. For the equations to be consistent, the theory requires the universe to have many more dimensions. Most versions of the theory require 10 or 11 dimensions in total. So where are they? We only experience 3 spatial dimensions, length, width, and height. String theorists have a potential answer. They say the other dimensions are there, but they are curled up, compactified down to a size so small we could never perceive them. The standard analogy is a garden hose. From far away, it looks like a one-dimensional line. You can only move along its length. But if you get very close, you see it has a second dimension. You can move along its length, and you can also move around its circumference. The second dimension is there, it's just small and curled up. String theory suggests that at every single point in our familiar 3-dimensional space, there's a tiny, curled-up shape of 6 or 7 extra dimensions. Our particles can't move in those directions, so we don't experience them. Only the strings themselves can vibrate within them. This sounds bizarre, and it is, but it's a mathematical requirement of the theory. And it leads to the next, even bigger problem. It turns out there isn't just one way to curl up these extra dimensions. There are countless ways. The math allows for maybe 10 to the power of 500 different ways. That's a 1 followed by 500 zeros, an astronomical number. Each one of these ways of curling up the dimensions would result in a different universe with different particles and different physical laws. This collection of possible universes is called the string theory landscape. Our universe, with our specific set of physical laws, would just be one of these possibilities. This is a huge problem. A good scientific theory should make specific, testable predictions. It should say, the world must be this way. But if string theory allows for a near infinite number of possible worlds, then it doesn't really predict anything. Whatever physical constants we measure in our universe, you can probably find a way to curl up the extra dimensions that would produce them. The theory becomes less predictive and more descriptive. It can explain why our universe is the way it is, but it can't explain why it isn't some other way. And that leads to the biggest criticism of all string theory has, so far, made no testable predictions. The strings themselves are thought to be so mind-bogglingly small that we would need a particle accelerator the size of a galaxy to see them. The energies required are far beyond anything we can dream of creating, so we can't see the strings. We can't see the extra dimensions. We can't test the core ideas of the theory directly. For this reason, some scientists argue that string theory isn't really science at all. They say it's more like a mathematical philosophy, it's an elegant and beautiful structure, but if it can't be tested or proven wrong, does it belong in the realm of physics? This is a fierce debate that's still going on, but string theory isn't the only game in town. There is another major approach to unifying physics, a rival theory called loop quantum gravity. Loop quantum gravity, or LQG, takes a completely different path. String theory starts with the particles of quantum mechanics and tries to fit gravity in. LQG starts with Einstein's theory of space and time and tries to make it quantum. The central idea of LQG is that space-time itself is not smooth and continuous, like a rubber sheet. Instead, it's made of discrete, indivisible chunks. It's pixelated. If you could zoom in to the smallest possible scale, a scale far smaller than an atom, you would see that space is made of tiny finite loops woven together into a network. These are the atoms of space-time. From this network, space and time emerge. Each loop has a minimum size. You can't have a distance smaller than one of these loops. You can't have a duration of time smaller than a tick of this cosmic clock. This immediately solves one of the big problems in physics. The infinities that pop up in black holes in the Big Bang are caused by dividing by zero space. But if space has a minimum size, you can never divide by zero. The infinities vanish. LQG is a more conservative theory than string theory. It doesn't require extra dimensions. Like, it doesn't need a whole symphony of strings. It's a direct attempt to quantize gravity. It paints a picture of a granular, chunky reality at its most fundamental level. But LQG has its own problems. While it's a promising theory of quantum gravity, it has struggled to incorporate the other part of physics, the particles. How do electrons and quarks and the other forces of the standard model fit into this picture of a pixelated spacetime? No one has figured that out yet. It's the flip side of string theory's problem. String theory is great at describing particles, but has a weird, untestable picture of spacetime. LQG has a compelling picture of spacetime, but struggles to include the particles we know and love. So we have two main paths, both brilliant, both incomplete, and both leading in different directions. And there are other more radical ideas out there as well. Some physicists think spacetime isn't fundamental at all, but that it emerges from something deeper, like the way the behavior of a fluid emerges from the interactions of individual atoms. Some think information is the most fundamental thing in the universe. The search is far from over. So let's step back. What would it even mean if we found it? If tomorrow a physicist wrote down the final equation, the theory of everything, what would change? First, it's important to understand what it wouldn't be. It wouldn't be an equation that could predict the stock market or tell you who to marry. It wouldn't be the end of science. It wouldn't explain biology or consciousness or economics. Think of it like knowing the rules of chess. The rules are simple. You can write them down on a single page. But knowing the rules doesn't make you a grandmaster. It doesn't tell you all the beautiful and complex strategies that can emerge from those simple rules. The game is still rich and full of endless possibilities. A theory of everything would be the fundamental rulebook of the universe. It would tell us what the pieces are, the strings or loops or whatever they may be, and how they move. But all the complexity we see around us, life, thought, galaxies, planets, is emergent. It's the result of those simple rules playing out on an unimaginable scale over billions of years. We would still need chemistry to understand molecules, biology to understand life, and psychology to understand the mind. Those fields wouldn't become obsolete. They would just have a solid, fundamental foundation to rest on. But it would change our perspective on everything. For the first time, we would know the ultimate laws of nature. We would know the answer to the question, why are things the way they are, in the most basic sense. We would understand the origin of the universe at the moment of the Big Bang. We would know what happens inside a black hole. It raises deep philosophical questions. If the universe is governed by a single, elegant mathematical equation, what does that say about the nature of reality? Is the universe, at its heart, just math? And what does it say about us, that a species of ape on a small rocky planet can even comprehend such an equation? It also touches on questions of free will. If all of nature follows a set of rules, does that mean everything is predetermined? If you knew the state of every particle in the universe at one moment, could you, in principle, calculate the entire future? Quantum mechanics, with its built-in randomness, seems to suggest the answer is no. The universe might have a fundamental element of chance that can never be predicted. But a final theory would have to give a definitive answer on the roles of determinism and probability in our cosmos. So, is there a theory of everything? We don't know. It's possible one exists, waiting to be discovered. It might be string theory or loop quantum gravity or an idea no one has had yet. It's also possible that there is no single, simple theory. Maybe the universe is just messy. Maybe there are different rules at different scales, and there's no single overarching principle that unites them. Maybe the dream of a final theory is a human desire for neatness that the universe simply doesn't share. Or maybe the question is beyond us. Maybe our brains, which evolved to find fruit and avoid predators on the African savanna, are simply not equipped to understand the ultimate nature of reality. A dog can understand the concept of a ball, but it will never understand the concept of calculus. It's not a matter of the dog not trying hard enough, its brain just doesn't have the capacity. Maybe we are the dogs in this scenario, and the true nature of the universe is our calculus. That's a humbling thought, but the search itself is what matters. The quest for a theory of everything has pushed our science forward in incredible ways. It has forced us to develop new kinds of mathematics. It has driven us to build incredible experiments like the Large Hadron Collider to probe the nature of reality. It has given us a deeper understanding of the cosmos, even if the final picture is still out of reach. The story is not over. Physicists around the world are still working, still calculating, still arguing. They are looking for tiny cracks in our current theories, small experimental results that don't quite fit. Because that's where the clues to the next revolution in physics will be found. The desire to understand, to find a simple explanation for a complex world, is one of the most powerful human drives. It's the drive that led the first humans to look up at the stars and tell stories about them. And it's the same drive that now leads us to build giant machines to smash atoms together. We want to read the book of the universe. We've deciphered a few incredible pages, but we think there's an introduction, a first page, that explains how the whole story is put together. We don't know if that page exists, but we can't stop looking.